All right. Hello, everyone, and welcome back to Calculus. So we are starting off Calc 2 by talking about U substitution. So our goal today, we know how to use the fundamental theorem of calculus to calculate integrals when we can sort of see that the function inside the integral is pretty easily a derivative. However, there have been times where, when we calculate a derivative, it ends up being pretty complicated and not easily recognized as a derivative of another function. So our goal today is to try to figure out some of those situations. In particular, we're trying to figure out how to undo the chain rule via integration. Okay. So, as a reminder, chain rule says that if I take the derivative of a composition of functions, f of g of x, then what I get is you get the derivative of the outside function, f prime, you plug in the inside function, g of x, and then you multiply by g prime of x. So if I want to rewrite this in sort of integral variation of this, I know by the FTC, what this is saying is that if I took the integral of f prime of g of x times g prime of x dx, then I would just get back to f of g of x plus c, right? Because that is my antiderivative, is f of g of x. And so this is the situation that we're wanting to be able to recognize and sort of go back and figure out what f and g both were in order to calculate our integral. And the sort of key that we're going to end up doing, oops, sorry, this ended up moving a little, is whenever we end up seeing an integral that has both a function g and its derivative g prime, then what we're going to end up doing is we're going to replace g of x with a variable u, and that's going to end up making our lives easier. Basically, it's going to help us identify what f should have been. And this method is called U substitution. Okay, so let's see an example of this in action. So we're asked to calculate the integral from 0 to 5 root pi of 3x times sine of x squared dx. Okay, and you can sit here and you can try the FTC and all the methods that we have so far. Not going to be super helpful. So what I'm going to recognize instead is that I have x squared and I have 3x. Now, 3x is not quite the derivative of x squared, but it's a multiple of it, so that's good enough. So this is kind of my key, my intuition that maybe I'm looking at U substitution. So I see a function and its derivative up to a constant. Okay. So according to our last slide, what that says is I should replace my function with u. So I'm going to rewrite this as if I let u be x squared, then I want to rewrite this whole integral in terms of u. So the easy part is, right, that's sine of u. Okay, and then I have x's elsewhere. I've got a 3x, a dx, and then really these integrands, even though it doesn't say there in terms of x, they are. It's measuring between x equals 0 and x equals 5 root pi. So I need to be a little bit more careful. So let's see. So if u is x squared and x goes between 0 and 5 root pi, then that means u goes between 0 squared and 5 root pi squared. So I can change these to being 0 and 25 pi. Again, just replacing my x's with the corresponding u's. Since u is x squared, basically I just squared both of my integrands, both of my bounds. Okay, so that's one of my issues. Then the other issue is I need to rewrite this 3x dx in terms of u's. And the way to do that is you come back to the definition of u, it's x squared. I'm going to take the derivative with respect to u on the left side and tack on a du. And on the right-hand side, I'm going to take a derivative with respect to x and tack on dx. So on the left side, take the derivative with respect to u, that's 1, and then tack on my du. On the right-hand side, I take the x derivative, so I get 2x, and tack on my dx. So in other words, what I'm saying is du is 2x dx. So the way that u changes is related to the way that x changes in this format. Okay. well, I wanted 3x dx, not 2x dx. So I can recognize that if I just multiply both sides of that last line by 3/2, I get exactly what I wanted. So that allows me to rewrite my 3x dx as that's a 3/2 du. So I can replace it like that. And at this point, I know that was like a lot of setup. However, at this point, we should be feeling pretty good because if you look at it, now that's an integral that you know how to do straight away from the FTC. There's nothing too busy about it anymore. So let's see. So I need to find the antiderivative of sine of u. So let's see, or 3/2 sine of u. So the antiderivative of sine is negative cosine. Don't forget your plus c because we've anti-derived. And then, okay, so we're looking at negative 3/2 cosine of 25 pi minus a negative 3/2, so plus 3/2 cosine of 0. Okay, 25 pi, let's see, so if we think about that, that's an odd numbers of pi, so we're going to be at cosine being -1, so this is 3/2. Plus, and then 3/2 times cosine of 0. Cosine of 0 is 1, so plus 3/2. And so in total, we should get an answer of 3. So the big key with this method is, again, we're trying to take something that looks a bit more complicated and get it down into something, so a complicated thing in x, and we're getting it down into a not so complicated integral in u. And the big key is we look for a function and its derivative in our x integral. Let u be the function, not the derivative, the function. And then translate everything else in the integral into things that involve u. So let's see a second example of this. Okay, so I'm looking for a function and its derivative, more or less, again, up to a constant. And it might not seem like we have that here, right? But if you think about it for a little bit, you can see that it would make sense to call 3x plus 7 the function, which would then say that 3 is the derivative, which again, we see up to a constant. So we are going to be able to do u substitution here. And per our hint, we should let u be the function. So we're going to replace 3x plus 7 with u. So let u be 3x plus 7. So then that says if x used to go between 0 and 10, then u is going to go between 3 times 0 plus 7, so 7, up to 3 times 10 plus 7, so up to 37. I'm not going to deal with my numerator for a second. My 3x plus 7, that's just u. And then I need to replace what I have left, which is 5 dx. I need to replace that by something that involves u's. So again, I'm going to take the u derivative of the left-hand side here and tack on my du. And that's going to be equal to take the x derivative on the right-hand side and plug in my dx, or tack on my dx. So I wanted 5 dx's. I now have a formula about 3 dx's. So if I multiply both sides by 5/3, I can see that 5/3 du is the same as 5 dx, and that's what I needed to replace, was the 5 dx. So I can, sorry, I can replace my 5 dx with a 5/3 du. Okay, and I'm going to rewrite that a little bit. So 5/3 times 1 over u du. Okay, hopefully this is very recognizable as an integral that you know how to do. So the antiderivative of 5/3 times 1 over u is 5/3 times the natural log of u. Don't forget your plus c because you've taken an antiderivative. And then evaluate at your bounds. So u being 37 and u being 7. So we get 5/3 natural log of 37. Your plus c's will cancel. So minus 5/3 natural log of 7. All right. Okay, so why don't you go ahead and try an example yourself? So I have both the answer and the example here, so maybe don't look at the answer yet. But go ahead and try to calculate the integral from 0 to 10 of sine of x e to the 4 cosine dx. And once you get done trying that, go ahead and check your answer against this. All right, fantastic job, y'all. See you next time.